is hydronic separation. Now, I call it hydronic separation, and the engineers of the world call it hydraulic separation. And if you read any book regarding hydronic separation, they always call it hydraulic separation. And this is part of my beef, that I prefer to call it hydronic separation, but let's call it hydraulic separation, because, you know, breaking up is always hard to do, right? But let's first look at how a pump works before we get into hydronic separation, which a pump only works by making a delta T, or a difference in pressure between its output and its input, or its out and in, if you want to call it that. And here in this application, I just chose 16 PSI on the outlet and 8 PSI on the inlet. We have this pressure set on the system at 12 PSI. So when this pump goes off, it goes right back to 12 PSI if there was any air in the system. But in the meantime, this is just circulating around. High pressure goes to low pressure. So please note that we're talking PSI, because that's an 8 PSI delta P, which 8 times 2.3, which sits 2.3 feet of head per PSI. It's 18.4 feet of head it's pumping out. But we really need to have an expansion tank somewhere in here to be able to handle it, right? So now we put an expansion tank in, and our expansion tank, as we've pointed out in previous ones, is your point of no pressure change. If it's set at 12 PSI, that's great. Here the pump's putting out, it goes right to 12 PSI to the tank and drops the entire system to 4 PSI, which is absolutely terrible. Same delta P, but now the system is dropped to a quarter of its actual pressure that you charged it to. Whereas if we just change that expansion tank position, now all of a sudden we have a 20-pound system and a short section of 12 PSI. So this is important for us to put our head around, that everything we do in hydronics is based on delta P, or a change in pressure. High pressure goes to low pressure in all applications. So we want to try to make our systems higher pressure to make the air smaller and to increase flow by 30%, but also most importantly, increase transfer of heat by 30%, which is amazing just to think that a small change in not what you put in, but where you put it. So that's important to just keep that in mind for the rest of the night. So here's the systems the way we used to be, right? So I'm going to get my highlighter out here, because I like to use a highlighter. And in days when I started in this business many years ago, and looking through the list, I was born before a lot of you, but not all of you. If you had your camera on, you would have seen me taking a sip. Anyway, so here's a standard boiler. We have a cast iron air scoop. We have an atmospheric ceiling mounted expansion tank. We have our circulators on the returns. We have flow checks on the supplies. And this is how I was taught to put boilers in. Now, these air scoops, of course, never worked. Just a brief note, because we never read the directions, RTFM first, that said you need 18 inches of clear pipe, straight pipe, before this air scoop to stop the flow from twisting. Realize that what comes into an elbow comes out of an elbow, and so you have two different velocities, or a whole bunch of different velocities, where the water on the inside is going very slow and the water on the outside is trying to keep up, going very fast, right? So it comes through here twisting like a son of a gun and doesn't smooth out until it gets right up here after 18 inches. Then it can go through and the air can actually get out. So, you know, we created our own need for a spire vent, folks, or a micro bubble air absorber. But in the meantime, back in those days, we used this to hook up our ceiling expansion tank. So any air in here would go up to the tank and refill the air. And we put our fill in there because we knew this was the point of no pressure change. Though what we didn't know is in this system, we increased the pressure from the outlet of that pump through the boiler up to the air scoop / expansion tank point of no pressure change. And then we dropped the pressure throughout the entire rest of the system. Now, this is an entire night just on pumps, and I'm not going to take anything away from Takeaway After Dark. I'll let them go through how pumps work exactly and where this is, but I need you to understand this concept. Now, when I started in this business, we were putting in little boilers, aka the Weil-McLean 68 series, to replace coal fire boilers that were the size of my Ford Expedition. So, you know, we had houses with water mains of 3 and 4 inch. They were originally gravity fed using coal. Massive amounts of water in there, cast iron radiators, and when we put these little boilers in, they would condense. Now, we don't want a cast iron boiler to ever condense. It creates bad blood. It creates sections cracking, sections warping. It creates all sorts of havoc. So what we used to do to correct that is put a bypass in. Now, folks, this was the early days of primary, secondary circulation. And if you could see my hands, you'd see one hand circling slow and one hand circling fast. And the slow circling hand is the boiler and the flow that's going through it, because it's going through much slower than it's going through the system, because you have two different flows. You have the flow that comes from the circulator, comes up to here, goes, rut-row, I path the least resistance here, so I'm going to put 70% of the water around here, and I'm going to let 30% of the water go in here. And that way the boiler can get up to 180 degrees and stop condensing. And this was the important part of that. And Jason, if you would please, after that explanation, would you launch poll question number 3, please?
Very Bob. Root-roo, I like that. I like to go root-roo. All right. Launching this bad boy now. What was the reason? What was Kyle? Go ahead, yeah, go ahead, Kyle. I was gonna read it. Go ahead. Go ahead, Kyle.
As you know, I never liked reading in school.
Yeah.
What was the reason? What was the reason for the bypass? Select
Yeah.
1. Allow the boiler to get to non-condensing mode. Reduce expansion noises in the system. Better combustion, or all of the above?
All right.
Is that you poured out that beer that you were drinking?
I was tapping on my glass to try to simulate expansion noises. So, Jason, what are the answers?
Well, let's give him, 59 said, oh, I'm loving this. This is going old school too. 59% allow the boiler to get to non-condensing mode. Yeah, you kind of right there. All the above 36%. 4 said better combustion. Well, if you read into that, number 1 is if you didn't do a boiler bypass, you would have scaling on the heat exchanger, which would affect your combustion. So I would have to say, I'm going to give that 4% an okay on that. But you should have went with number 1. 61% changed their answers to allow the boiler to get to non-condensing. I mean, the only thing with that is you get that chimney.
Jason,
Depending on the size of the chimney, if it's not lined, you're gonna have scaling in the heat exchanger.
all the above is actually the answer on this one, because if we get rid of the moisture inside and get rid of the condensing, then the oil can actually do its job and our stack temperature can be where it is, and we can actually burn oil at a good rate. So it's all the above.
Voice came from, where'd that come?
So cool. All right, end it up.
It's kind of a tricky one there.
I know. I have to be tricky. So here we are now. We're going to pump away. We're going to get rid of the ceiling expansion tank. We're going to put a microbubble air absorber on, and we're going to do the system using old school bypass ways to show how we should be piping it in. Those of you who do commercial work know for a fact that you will never see a base mounted pump on the return of a boiler, for God's sake. You always see it off from the supply pumping to the system away from the expansion tank, and you know that. There's multiple reasons why we put them on the return, and part of it was back in 1901, we switched from steam to water because, oh my God, we were blowing up boilers because people didn't know how to put a fill on a steam boiler. And we didn't have seals to be able to handle 212 degrees because that's what everybody ran their boilers at, because that's what steam was at. And, it's all fine and good, but the bottom line is the circulators need to be on the supply. So the system is high pressure. What's that?
Now that picture right there, go around that expansion tank and that feed. That's perfect, dude. They sell those in kits. You can buy them.
Okay. Jason, I don't care about the kits right now. I got a lot of shit to go through. So
come on.
To cut you short, I understand the kits, but we just need to know where we got to place this shit right now. So now we got into a thing called outdoor reset. Now this is where we lower the temperature of the water or the amount of thermal energy we're sending out to the house as the outside energy goes up, meaning when it's 70 degrees outside, we could send 70-degree water out because there's no heat transfer. You don't give a shit. But as it dropped down to, I'm in Philadelphia, so my design day is 14 degrees, and I design 180 to 14. So I could go from 70 to 180, And as the temperature outside drops and we pass more thermal energy through the wall, I could put more thermal energy into the tubing, so into the fin tube to extract the heat out of to make up for the amount of energy going out. And it's just the way we do it. More heat's needed, more thermal energy is going out. More thermal energy means higher temperature water. It's pretty easy, but with a cast iron boiler, you couldn't do it directly. So what we did back in those days is we created true primary, secondary circulation, where upon any call for heat, the circulator on the primary loop would start to circulate. Round and round it goes. And we'd have a sensor somewhere up here on the supply line that saw how much heat we had, and it would turn the boiler on and let the boiler get to 180 degrees and then start the circulator up and inject that through these two closely spaced T's in the system to bring it up to the temperature we needed, allowing the boiler to be over 160 degrees so we don't condense, because we knew that if we returned below 140 here, the boiler would condense. So at least 160, it would inject the system temperature, off would go the zones, again on closely spaced T's, which I'll explain in a second. And when we had a call for domestic heat, the circulator on the loop would turn off, the circulator for the indirect would come on and bring the water back around. The boiler would continuously run at 180 degrees and everybody was happy and off we went. Now, the reason for the two closely spaced T's is, as we discussed, a circulator works by circulating water by creating a delta T, or a difference in pressure. And when these T's are 4 pipe diameters apart or closer, that's 4 pipe diameters of the branches, when the water gets to the first T and gets to the second T, it's the same pressure. If this circulators are not running, it's the same pressure on both T's. So it just keeps on going around. It just goes around and around and around until we turn the circulator on and create a drop in pressure. And now the water goes up and around and back in and up and around and back in. And it's the way a circulator works. So back in those days, we called this center loop. Some people call it a racetrack. Center loop. It was the primary loop, and the boiler and the zones and the indirect were system zones. Now we call these system zones, this the system loops, this the boiler loop, and you still have the indirect loop. But this is how we did outdoor reset and save people 14% of their energy bill a year by using a TechMark control, something silly like this 361, that would control this, protect the boiler, and give you the right amount of temperature for the zones. And upon domestic hot water would say, you guys go off, I'm coming on, everybody goes to 180 and off we go. And that's where primary, secondary came in. And if you ever want to read an interesting book, Primary, Secondary Made Easy by Dan Holohan, which I'll give you these references later, is a phenomenal book for you to read. And so is a book called Pumping Away, which explains the expansion tanks. But now let's move on here. So now let's make this a little bit bigger. Now we have a bigger boiler. We got all sorts of zones here. We got circulators. Now we're going to reverse our flow here. We're going to go around this way instead of my other zone. Now I have an indirect zone. I have boilers. I have zones set up here on outdoor reset. I got a radiant heat zone, and everything's being protected. And the boiler is just having a grand old time, just running between 160, 180, injecting through the circulator, just pumping up, depending on the temperature we need. And everybody was happy. This is primary, secondary as we know it. It's pretty easy, but primary, secondary required you to have a circulator on that circular area, on that racetrack right here. It required you to have this circulator. You had to do it. So the two closely spaced T's, which is right here, here's my primary circulator going through the loop. And it would get to the first T and say, oh, no pressure drop, and keep on going around the loop until the circulator came on to go up to the load. So we had our primary circulator and our secondary circulators. Hopefully this is clear as mud to you guys on the phone, because on this line, because I can't use my hands to show you anything like I normally do, thanks to whatever happened in my GoToWebinar. But again, we'll figure that out. But the key there is 4 pipe diameters, and that's 4 pipe diameters, not of the main pipe, which is handling 100% of the flow, but of the secondary loop going off to the system. So if this was 3/4 inch pipe, these T's should be less than 3/4 3/4 of 4, so it'll be 3 inches apart between these two tees, which is dead nuts together on the tees, as you know, especially at Pro Press today. So that's where that comes in. So please note, for closely spaced tees to work correctly, you must have 18 inches prior to the return tee on the direction of flow, what's coming in, you have to have 18 inches prior to the first tee you're getting to, and 6 inches after it. So you have to have, coming to the first tee, you have to have 18 inches and 6 inches past that. Now, this is written for a condensing boiler, so it doesn't count. This should actually read 18 inches prior to the supply tee and 6 inches post the return tee is what it should be for a primary secondary loop. So keep that in mind, because if you don't have that 18 inches straight, you have that cavitating flow that will create a pressure drop, and you'll actually get ghost flow. You'll actually get ghost flow. Let me go one back further. You'll actually get ghost flow if there's not 18 inches. If there's not 18 inches of straight pipe, you'll actually get ghost flow and create circulation through this when this circulator is running if you don't have that straight pipe before it. So here's primary, secondary, the way we used to do it. Now, this is a condensing boiler now, so we don't need to have a primary loop. But when this system was originally put in, it was twin 200,000 BTU cast iron boilers. And we see the primary pump here that would circulate the water around and around and around. And this pump would go off when the indirect pump came on and would pump through the boiler and back through. We'd only inject the boiler as needed. But now that it's a condensing boiler, this boiler goes up, outdoor reset. It keeps this loop at an outdoor reset temperature, but we didn't want to get rid of this primary loop. And you can see these loops going out, the zones going out on as close as we get them. Look how close those tees are. I mean, they're soldered right next to each other. Yes, this is before ProPress. And yes, the person who did this loop screwed up, and this loop is back to being the right way. So this is primary, secondary as we knew it in the 80s and 90s before we came out with condensing boilers. Now, let me show you a couple pictures here. Here's the racetrack that an old friend of mine used to show. He would call this the racetrack, this primary loop, and off we go, woo, right? And here's our two closely spaced tees on boiler 1, two closely spaced tees on boiler 2. Here's a zone over here with two closely spaced tees, a zone up here with two closely spaced tees. But they broke my primary rule, which is they don't have 18 inches of straight pipe up here in the corner, and they don't have 18 inches of straight pipe here, which means anytime this circulator runs, it's going to create flow in this loop, and it's going to create flow through this boiler, whether it wants it or not. Not a lot of flow, but enough flow that we don't want. These tees should actually be over here, just past to the right-hand side of that yellow square to make it right. So, and of course, here's your two closely spaced tees coming off of your atmospheric boilers to make it happen. So this was primary, secondary, like I said, of the 80s and 90s. So now this is how we do it with modulating condensing boilers. We don't care to protect the boiler from condensing, because if we did, we'd just call it modulating boilers. But we call them modulating condensing boilers because we want them to condense. So here's our circulator that's going to create our differential, so we make sure we have enough flow through the boiler. And here's our zone pumps that are going around. Of course, they're pumping away from the point of no pressure change, aka the expansion tank, so we have a higher system pressure, and this pump can do its job. Now, this pump has multiple reasons to be there. One is we've gone from a huge area of heat transfer in cast iron boilers to a small area in the condensing boiler. So we need to move the water at a given rate to make sure we don't boil the water. The other reason why this is this way is to make sure, especially in a water tube, we have the right amount of flow so we don't scale up. We try to prevent scale inside the tubes so we have enough flow, and that's where this primary, secondary came in for condensing boilers. Now, people say, oh, well, you know, my primary pump is, I don't think it's the right size. And I say, well, which one's your primary pump? And they say, well, what do you mean? I said, well, do you have a primary loop? Well, yeah, that's the boiler. No, it's not. See, we no longer have a primary loop. We now have a system, set of moose antlers, if you want to call it that, with a supply and return header. and we have 2 closely spaced tees, which we can do multiple ways, which we'll get into going to the boiler, right? So this ensures that we have everything. So we have boiler pumps and we have system pumps. So when you call up and say to me, hey, Wheels, what size primary pump do I need? I'll say, well, which one are you calling the primary, the system pump or the boiler pump? As long as you did it our way, we can go from there. Now, when you add an indirect water heater to this, we break it in between the circulator and the modulating condensing boiler, so we can turn the circulator off to the boiler for the system, turn the pump on for the indirect, let the boiler go to 180 degrees, circulate 180-degree water through here. When that's done, this pump goes off, the boiler pump comes back on, circulates waters up to the closely spaced tees, and the system can go back to having outdoor reset temperature. So that's closely spaced tees, much like shown right here. Now, I've drawn it this way for a particular reason, because closely spaced tees are not the only way you can do this, but here we are with closely spaced tees, and here we are with the drawing with closely spaced tees and having the indirect water heater next to it. You can see if I now have included a magnetic dirt separator coming back in. I have the system flow going out. I threw a radiant floor on the end just for the hell of it, so that we can have some fun with this, right? So here's primary, secondary using closely spaced tees. Now, the advantage of using closely spaced tees is it's sized based on the highest flow rate between the system or the boilers. That means that the size of this pipe going through here is sized based on either the system flow or the boiler flow, whichever one is greater. The advantages of closely spaced tees are space. They're very small. Adaptability. I can put them anywhere in a system. I just have to tie the supply and returns together going off on an existing system and throw 2 tees next to each other, and I can blow my boiler into it. They're not very expensive. I'm saving money. So they work. Now, a lot of people are starting to use low loss headers. So low loss headers are these very famous little things that look like, well, why am I even talking about low loss headers and telling you what they look like when I can show you? So here's some of the floor mounted commercial low loss headers that I've seen. Here's a floor mounted flanged one from Califfi. Here's a large, I would say large residential, light commercial Califfi with a magnetic separator, which we call SEP4. So this is going to do multiple things as opposed to this one, which is just a low loss header. This is actually your micro bubble air absorber, your dirt separator, your magnetic filter, and your primary secondary loops. So that our boiler is attached to here going around and around and around, and our system is tied to here going around and around and around, and it just pulls everything through if it has to, and pulls everything through here, and gets rid of your air, gets rid of your magnetite, gets rid of your dirt, and it's a phenomenal unit. So it's four things in one. So these are phenomenal little things. The biggest one I've done of the floor mounts, the biggest I've ever supplied was an 8-inch flanged, huge system. And these are based on the same thing that your closely spaced tees are. And that's the flow rate based on the maximum flow rate of either the primary circuit or the secondary circuit, whichever is greatest. So Califfi has chosen to call the boiler, I guess, the primary circuit, and the system the secondary. Oh, wait a minute, no, they could have called the primary circuit the boiler.
Look at 8
system, and the secondary the boiler. Oh, we don't know which is which, but it's just one side or the other. Whichever one is greater flow is what you have to list your GPM through, which is listed right here. Now, this is part of the handout that you have in the handout section. Is this? I copied this right off of it, and you size it by GPM. So if you have a 20 GPM on the system, but only 15 GPM on the boiler, you're still going 1.5 inches because 20 GPM doesn't go into 18. You got to go up to 26. So you have to size them accordingly. I'm amazed at the number of 399s I go on. That's 40,000 BTU, which means your system should be running at about 36 gallon a minute, which would be 2 inch. And you guys are putting 1.25 inch low loss headers on. And you can't figure out why it's not getting the dirt and the magnetite out and the air out, it's because your flow rate is too effing much. And again,
Holy-
that F does not stand for factory. If you move the water too fast, it can't do, the low loss header cannot do its job.
Holy
So-
moly, look at it. 8 inches, look how much it does.
Oh, yeah,
Holy
baby.
shit. That's some
So,
serious. Whoa.
oh yeah, baby. The advantages of a low loss header are smoother flow rates. You don't have so much conversion between two closely spaced tees. You don't have the water going backwards on some applications and forward on other applications, and it creates a nice even flow. If you use a SEP 4, it can do multiple jobs like air removal, dirt separation, magnetic filtration, as well as separating your system. And sometimes it works into the scope of piping much easier. And you don't have to worry about 18 inches of straight pipe going into it, because you're going into there and that low loss header is creating a flow that it needs. So it's really quite a nice way to go. And I really, on my son's place, I put a SEP 4 on so I didn't have to use a low loss header or a magnetic separator, and it works fabulously. And you can also get them insulated so that big mass of steel doesn't lose any heat. So it actually works to your advantage all the way across the board. So here's a nice big system with 3 boilers, a hydro separator in the middle. You can see the indirect water heater coming off first, so we can turn off this circulator when it calls for this, and then we can turn the other system circulators on. This happens to have a variable speed circulator here to inject whatever temperature we have here injected in, so it can have a outdoor reset or its own temperature here for one radiant zone. This is another radiant. Actually, this is snow melt up here that we're going through a plate heat exchanger. So this is doing all sorts of shit. And if you get into jobs like this, I would love to be able to hook up with you, because we have the controls and the knowledge to do it. Our boilers today have multiple temperatures available to you to be able to use, depending on what's calling here. And a lot of times in this application, we could actually put all these pumps onto a TFTN and work very harmoniously together and still come up with the right temperatures that you need.
I mean, that separator, I have that SEP 4. That thing saves so much time. It
Oh, yeah.
does.
So
Dude, how much do you think the fittings cost? Just off the top of your head, it's got to be a couple $100, at least
yeah.
3 or.
nah, a couple teas aren't that expensive. So, but now let's go to the third way to do hydraulic separation. The third way to do it is through a buffer tank. Now, here I show a buffer tank. I didn't put the indirects on either one of these two, which would come off between this circulator and the boiler, and between here and the tank, and we'd have an indirect water heater. And here we have a buffer tank. And we come out of the buffer tank with the system pumps, and we come back around. And the nice thing is, on the new TFTN, we actually have a buffer tank pump and a place to put your sensor on, so it can actually maintain whatever temperature you want on the tank for you. The biggest problem I see with these is people oversizing them. By the way, I cheat, and I did draw this in so you guys could see the domestic hot water heater coming in, and I did cheat a little bit by doing this way. But I actually designed with a company, and I won't mention their name because you could probably read it. I helped them many years ago in designing buffer tanks, and they said to me, well, we're going to come out with an 80, 100, and 120. I said, no. They said, no, what? I said, you're going to start at 10 gallons. They said, why? I said, because most systems don't need more than a 20 or 30 gallon tank. And in probably 70% of the ones that I do, I can get away with a 10-degree tank. And they said, how do you know that? I said, well, it's easy. You just have to put it in the formula where your volume of your tank equals, on the top line here, the time that you want the boiler to run times the heat source BTU less the load that you have on your smallest zone, divided by 500 times delta T, or your difference in temperature on the boiler that you're going to be turning it on and off at. So you get into these sizings and you go, wow, well, then what do I need? So let's take this equation, and let's say we have a 75,000 BTU output boiler. Our smallest zone is 2,000 BTUs. It's a little baseboard zone out in some guy's, I don't know, office, right? And it's just 2,000 BTU. It's 4 linear feet of baseboard, right? And we want our minimum runtime 10 minutes because the boiler you're putting in wasn't built like NTI and made to short cycle. It was something that you need runtime on. And we're going to turn the boiler on at 120, but we're going to turn it off when it hits 180. And these are just arbitrary numbers I put out there. And so we take we fill in for V, we take our 10, which is our number of minutes. 75,000 is the BTU of the boiler. 2,000 BTU is the smallest zone. So 2,000 less 75,000, that'd be 73,000 times 10, and divide that by 500 times 180 minus 20, or 500 times 60. And when you multiply that all out, you find out you need a 24-gallon tank, which in the Vaughn world would be a 30-gallon tank, because they make a 10, 20, and 30. But I figure these jobs all the time that I need a 8-gallon or a 15-gallon. Rarely do I need an 80-gallon tank. And I know that some people believe that having a indirect that's exactly opposite of our indirects, that the tank holds the boiler water and the system water goes, the domestic hot water goes through coils, and that this is going to save money because you're going to heat up this 80 gallons worth of tank, so you have domestic water. And the problem is I can no longer now use it for outdoor reset, because they might want hot water at some time, which means I have to maintain a temperature on that tank that's going to give them the GPM that they want. And this is a very hard thing to do. So I caution you on doing that using certain people's indirect water heaters. I would never use one of my indirect water heaters as a buffer tank. Why would I, when I can buy a nice steel insulated buffer tank like a Vaughn that now solves many problems? By problems, I mean, now all of a sudden, let me go back here because I forgot to put this slide in. This tank is now my dirt separator. All my dirt in the system is going to fall out here if it's not magnetic and caught by the magnetic filter. And it's going to be my air release. And it's my primary, secondary unlinking, right, for my hydraulic unlinking. And now all of a sudden, I get rid of my air, and everybody is a SEP 4 on steroids, if you want to call it that, except for I did need to put a magnetic filter on it because this has no way to do that. So tanks have a great usage in certain applications, especially, in my opinion, cast iron boilers that are probably 3 to 4 times the size they need to be and can't short cycle, shouldn't short cycle, and you beat the crap out of them, when we could just put in a tank to store that energy, and then you wouldn't have that issue. So use the formula. If you don't have it, you can take a picture of that real quick and it will give it to you. Once you use this formula once, it's cool. I have in the past built a spreadsheet that does this for me. I couldn't find it today, or that would also be in your resources. Seems to be the camera god and the resource god was fighting me for 8 hours today, so I apologize. And let me give you some resources. So resources, Dan Holohan, author, retired. Dan's a good friend of mine. If you haven't bought and read Pumping Away, it changed my world in hydronics.
Yeah, it did.
It's a cheap book. It's under 30 bucks. It's available at I'll give you that resource in a minute. His other book that's a fun read, Primary Secondary Made Easy by Dan Holohan. And all of these are available at www.heatinghelp.com, or of course on your favorite Deliver It Tomorrow company, Amazon.
Deliver It Tomorrow company. It's funny.
So some of my resources, like taking, instead of drawing out and having to figure out how to write a formula in PowerPoint, I did copy directly from one of my most favorite teaching books that I've used in multiple tech school classes, Modern Hydronic Heating by John Siegenthaler. He now has modern hydronic heating and air conditioning. No need for me to have the air conditioning, although now that we're getting into air to water heat, or air to water heat pumps, I guess I do need it a little bit. But my Modern Hydronics by John Siegenthaler, what a great resource it is.
That's a good read.
If you don't own it, get it. Takeo Training and Takeo After Dark. My good friends, Johnny Barba and Dave Holdorf run the training. Timmy's there with them for Takeo After Dark. If you haven't done their class, I think it's a 5 Tuesday. It's either Tuesday nights or Wednesday. I think it's Wednesday nights now. 5 Wednesday nights in a row, and you learn everything that Jimmy DePalma can teach you here in the East Coast and more on steroids. And if you ever had the opportunity to go to the Takeo factory training at Takeo, just get up and do it. Just don't even ask questions, just go do it.
That's
And the
worth it.
last thing, Califfi Hydronic Solutions. My good friend, the Roars, work there. Hot Rod and his son work there. They do a fabulous job at training. They run a phenomenal show. You have Coffee with Califfi. And then the other great resources, and if you haven't subscribed to it, is Hydronics Magazine. You can get it electronically or in paper print. They, they are not, I mean, obviously there's Califfi ads in it because they print it, but there is all hydronics, much like our Thursdays, all hydronics, not specific to any one boiler or one type of boiler, but phenomenal magazine, and they're located at www.califfi.com. So,
Steve,
what?
you mind if I jump in here? I want to throw one name. I don't know if I heard it. Cody Mack, good guy for Califfi. He's done
Yep.
a lot of.
Cody's a good boy. So, Jason, if you would, release the last poll question.
All right, buddy. I'm getting on it right now. Here we go. Poll question. Last one. All right. All right, launch it. Which do you prefer? Closely spaced tees, low loss header, buffer tank, or it depends? I don't know. I like a buffer tank.
I'm not a lover. I love the low loss headers, and I know the questions that I'm going to be asked about certain manifolds, and we'll answer them in a minute. But in the meantime,
but here's why I love a buffer tank. If you have microzoning, it's going to cure all those issues. I love that for a buffer tank. I mean, and it drops the size of the boiler too. Oh. But you're right. You don't got to get crazy. You don't got to get crazy. 10, 20 gallons, like you said, 30 gallons, you're good to go. All right, where we at? Closest space tees, 13%. Low loss headers at 38. I can see that. I mean, these guys can bang them out real quick. We used to do it in the old days at Dieters. 6% in buffers. Well, once you experience a couple buffers, you'll change your tune. And 44% says it depends. I don't know. I'm a buffer lover. Makes that boiler not run so much. It's gonna eliminate your boiler runtime. It's gonna eliminate the wear and tear in your boiler components like the igniter, the gas valve, the fan. Just throwing that out there because the boiler's not gonna have to cycle until the buffer tank calls. You drop that size tremendously. Let's see if they change it.
So, all right. So one last thing, and you can end that poll if you want.
Done, my man.
So I did this because what I'm about to say is not politically incorrect, but if you notice in all my drawings of closely spaced T's, they never look like an H. They look like a double T. And I have a problem with people who want to make H's out of their connections because your flow is always going to fight itself.
All day long.
If you remember my slide that says your closely spaced T's should have 18 inches before it gets to the first T and at least 6 inches out of the second T. So in the direction of flow coming across, 18 inches coming into and 6 inches going out of your two closely spaced T's. This is intentionally said this way because an H does you no good. It's going to fight itself and create cavitation between it and turbulence that you won't expect. So please, those of you who are using H's, please stop and please start using closely spaced T's on a horizontal bar. It just requires you to move your piping a little bit. It's not going to cost you any more copper. You just have to design it properly.
Listen, if you don't want to go and make it, you can go buy the Webstones or whatever these manufacturers. They make them. You don't have to, if you don't want to go and do the work, which, you know, it's artwork. I consider artwork, but if you don't want to do it, you can buy them, Steve. You know, you sold them for how many years?
Yep. So now a couple questions I wanted to answer here. One question came through to me, what program am I using to do these drawings? Those of you online, I will tell you, and let me go to my next page. Now let's just leave this intentionally black.
Are you using Visio?
I use Vizio, and if you ever buy Vizio, it's a Microsoft product now. It used to be standalone, but if you buy Vizio and if you email me and say, hey, Wheels, send me your stencils, I will send you the stencils. Stencils are also available. All the Taco circulators and stuff that I showed were stencils I got from Taco. Taco has all their wiring schematics on stencils, so you can do wiring schematics. Tecmar, I actually physically drew back in the day all the Tecmar stuff I used, but I believe they have stencils now. But I have stencils of all of our products and all of our tanks, and I'd be more than happy to send them to you if you buy Vizio. What other questions came up, Jason, that we need to know? Kyle, anybody?
I'm looking at them right now. Hold on.
Oh, so the question is, what is an H? Let me see if I can.
I may have a picture of that for you.
Yeah, do you have a picture of an H? I mean, I have.
Oh, yeah, I have a picture of an H for you. I got.
Let me see if I can find it.
It, Big Daddy. You go ahead and talk. I'll go ahead and you got the.
So you
the face for
understand,
Ray.
if you ever installed a TX boiler, we used an H underneath, but the reason for that was because we had a very high velocity pump inside, and we don't care if your system pump increase the input through the boiler a little bit. It's also the same reason why our closely spaced T's now are our headers for our boilers that you can buy pre-packaged. Also are 14 inches apart because it's easy. It comes straight down and out of it, but we don't care. We're not trying to ward off ghost flow in a system like we were on a primary loop creating ghost flow. So we don't care if you create a little bit more flow through our boiler. It's okay. Or if the boiler's not running, if the system's putting a little bit of hot water back in the boiler, we don't care. More likely what it's going to do when the boiler shuts off on temperature, your system flow is going to have just a little bit of flow going through our boiler that will actually bleed off some of the heat. So we're actually not opposed to the way we do our pre-packaged manifolds that come out of our boilers. Now we call them low loss headers. They're not really, they're manifolds, but you guys all refer to them low loss headers, so we can't refer to them any other way, really. So did you find that H picture yet?
Yeah, I'm sending it to you right now.
Well, why don't you put it up on the screen? You want to share your screen?
No, I got to send it to your email.
Oh, then I got to open up my email, don't I?
Wait, hold on. It's on the way, so you should be good.
What?
Well, I don't understand the camera deal. It's so weird.
I'll figure it out. I'll figure it out this week.
Oh, never seen it before. It said, so it's coming from Vermont. So just pull that up there. Yeah. The old H. The old H. There you go.
Well, that's kind of an H. That's a T and an H, but a true H.
Oh.
This is no way to do it either. And let me see if I can make this bigger.
Yeah, can you make
A
that?
true H would have the T vertically here, which is even worse than what we have here. I was always taught you can never do this, and you can never. So a true H is coming up through here with the T's in between, so that your flow's all trying to get through this cramped little shithole. You just can't do it.
People do things for, I think they're going to do it to save space. But at the end of the day, you come off the bottom of the boiler with 2 drop pieces, at least 10 to 12 inches. Boom, put your T's, crossover piece, put a valve in there. If you have an indirect, boom, come out, you're all good. I don't understand.
So,
and
somebody made a statement that that you can downsize your boiler if you have a buffer tank, and that's a fine edge, boys and girls.
Be careful.
You can store BTU in a buffer tank, and if you don't know, you're going to learn goddamn buffer tanks when we go air to water heat pump, because you're going to need to store the BTUs in a storage tank that's insulated. So this is a buffer tank is going to be part of your world. So if you don't think it's going to be, get used to it, because it's no longer a buffer tank. Now it's a thermal storage tank. So you can, but if you have a catastrophic failure, meaning that you're out of heat for 3-4 days, and you have to try to heat that tank and heat the house, it's never going to happen. So, but most people don't size their boilers correctly anyway. So, yeah, you just can't do it.
He's
Thank you,
like,
Billy Silk. I love you.
you're right.
But anyway, cool. What other questions we got out there? I'm trying to scroll down here and see what we got. So I know somebody out there loves to use the reverse indirect, AKA TurboMax, and you can make them work. And I'm glad you do. And I'm glad it's successful. I'm not saying it's not. It is an option. But for me, it's not an option unless I have to have that kind of water. And then I'm not using it as a buffer tank. I'm using it as a water heater. So,
Let's see here.
so does the H make any more sense to the boys that asked, the guys who asked me what an H is?
Oh, Jason.
Cool. Thank you, Matt. I do appreciate the answer. So I try to avoid H's on all applications if possible. I had a commercial job going the other day. They built an H, and absolutely at 65 gallon a minute, I'm not going to allow you to put 2.5-inch H in. Not going to happen. We're going to have way too much flow out in the system with base mounted pumps to deal with the boiler, and it's just not going to work. So you're going to get flow through all your boilers at all the wrong times. The circulation is going to fight itself. And literally using the same amount of copper and just moving to where the T's were located coming from the boilers, it solved the whole problem. Of course, a low loss header would set to solve the problem, and so would a buffer tank. You won't have to worry about closing space T's ever again. So, yeah, Matt, I've seen a ton of them in the field. So anyway, it's been fun, guys.
Thanks for watching the video today. If you'd like to check out more videos, see the link below. Don't forget to like, share, and subscribe to our channel for all the future updates. And also check us out on Facebook, LinkedIn, and Instagram.